What if I told you there's a way to make your programs run faster without touching a single line of code? No need for rewrites, no need for fancy algorithms, just a switch. A magic command that can transform your code into something much more powerful. Stick around because today we're diving into Clang, a compiler that's capable of far more than just compiling your code. But what's the secret behind it? Okay, let's start simple. You've probably heard of compilers like GCC, but have you heard of Clang? It's part of the LLVM project and is known for producing high-performance executables. But here's the kicker. Clang does more than just compile. With its optimization features, Clang can take your basic code and make it run faster, use less memory, and even improve code readability without you lifting a finger. But how? That's where it gets interesting. Clang has an arsenal of optimization flags, each carefully designed to squeeze out every bit of performance. Let's start with O1, O2, and O3, which are different levels of optimization. At O1, Clang starts with basic optimizations like dead code elimination, which means removing any code that is never used, like functions or variables that don't affect the output. At O2, Clang takes things further. It does function inlining, which means it replaces small function calls with the function's actual code to avoid the overhead of jumping to another memory location. It also optimizes loops, making them more efficient by minimizing unnecessary operations. But at O3, things get really aggressive. Clang optimizes memory access patterns, so how your program accesses data in memory so it can better utilize the CPU cache and reduce wait times. It also uses SIMD, which stands for Single Instruction Multiple Data. SIMD allows the CPU to perform the same operation on multiple pieces of data at once, speeding up tasks like graphics rendering.
Speculative inlining or branch prediction optimization is a compiler directive or a hint used to inform the compiler about which branch of a conditional is more likely to be executed. This information helps the compiler and CPU optimize the flow of a program to reduce pipeline stalls and improve performance. The compiler uses this information to reorder instructions, optimize instruction cache usage, and crucially optimize branch prediction for the CPU. It's called speculative because the CPU speculates which path is most likely and then prepares the pipeline to execute instructions for that path in advance, avoiding delays from incorrect predictions.
Now here's something a lot of people miss. The ffast-math flag. What it does is it tells Clang, go ahead, take some liberties with math operations. It allows optimizations like ignoring precision and rounding errors to make your code faster. It sounds risky, but it depends on your use case. In scientific calculations where absolute precision isn't critical, this flag can speed up your programs dramatically. But if you're working with financial systems or any area where precision matters, maybe not so much. Now let's talk about something that could change the way you think about compiling. Link time optimization, or LTO. It's a feature that allows Clang to optimize not just individual files, but the whole program during the linking phase. Instead of treating each file as an isolated unit, LTO gives Clang the chance to see the whole picture, allowing it to apply optimizations across the entire program. With LTO, Clang can inline functions from one file into another, eliminate redundant code across files, and generally squeeze out every last drop of performance. The catch is that it makes the compilation process take longer, but the payoff is huge. This is the big one, Profile Guided Optimization, or PGO. It sounds complicated, but stay with me here. PGO works by running your program, collecting data on its performance, and then using that data to guide Clang's optimization decisions. Essentially, you run your code a little bit first, and then let Clang use that knowledge to optimize how it's compiled. Think of it like fine-tuning your car's engine after a few test drives. PGO allows Clang to make smarter decisions, like which branches of code to keep and which to discard based on real usage. The result is that your program can become much faster because Clang has tailored it to the actual workload. Now that we've covered the theory, let's take a look at what this really means in practice. Imagine you're working on a large project, a game engine, a web server, or even just a massive data processor. You've got your basic code working, but you need that extra push. How do you get it? With a few simple flags, we can unleash Clang's full power, just using O3, ffast-math, and adding link time optimization, or LTO, could make your code run 10% or 20% faster.
But when you combine all of it, optimization flags, LTO, PGO, you're looking at an entirely new level of performance. So how fast can you really go with Clang? It depends. It depends on the flags you choose, the complexity of your code, and the problem you're solving. But here's the best part. Clang does all of it automatically. You just have to know where to look and what to ask for.